All right, so we're going to look at homework 8, problem number 1. So we're going to let alpha equal set A, which maps to itself, and alpha and A is a finite set. We want to prove that if alpha is 1 to 1, if and only if alpha is onto. So we're going to have two definitions. One is that alpha is 1 to 1 if alpha of x1 is equal to alpha of x2 implies that x1 equals x2. And alpha is onto if for all y in A there exists an x in A such that alpha of x equals y. So we're going to start first by showing that if alpha is 1 to 1, then alpha is onto. So we're going to use contradiction. So we're going to start by saying that we're going to assume alpha is not onto. So therefore, for all y in A, there does not exist an x in A such that alpha of x is equal to y. So we can write out set A by putting y in it. We know y is an element of it. And since there are n elements in A, there are going to be n minus 1 spots remaining after y takes up one of the spots. And y does not equal alpha of x. So by the pigeonhole principle, since we have to fit n elements into n minus 1 spots, one of them is going to have to double up. So alpha of x sub I is equal to alpha of x sub j. But x sub I does not equal x sub j is a contradiction, so therefore alpha must be onto. So now we'll go in the opposite direction. We're going to say that if alpha is onto, it must also be 1 to 1. So by contradiction, we're going to assume that alpha is not 1 to 1. So therefore, alpha of x1 equals alpha x2, but x1 does not equal x2. Now, since the number of elements in alpha is less than or equal to n minus 1, we know that since alpha has at most n minus 1 elements because 2 of them had to double up, at least 2. But this is going to be a contradiction because since we know that it's onto, there exists an x for every y. All right, but since the size of A is n elements, there aren't enough elements if the size of alpha is less than n. So that's where we ran into that contradiction. So therefore, alpha, write that here, is 1 to 1.